All right, 5253. We are going to talk a little bit more about parallelograms, and we're going to talk about some properties that happen when you have parallel segments. Pretty much this entire chapter deals with a lot of parallel segments and then quadrilaterals. Okay, so those are the things we're mainly focusing on. So today we're going to talk about how to prove that a quadrilateral is a parallelogram, and then some theorems about our parallel lines. I didn't put a bunch of proofs on the notes just because, well, number one, I want you to practice them in the homework, but it's really similar to a lot of the things we did with the triangles, right? Proving sides are congruent, angles are congruent, things like that. So a lot of those same things will kind of apply. So we have a few theorems here, and these are theorems you're going to use to prove that a quadrilateral is a parallelogram. So you will be given four-sided shapes or maybe quadrilaterals within quadrilaterals, and you have to prove that they're a parallelogram. Who can refresh our memory of what makes a shape a parallelogram? There's one like key property. Logan? Yeah, both of the sets of opposite sides are parallel. So both sets of opposite sides are parallel, then it's a parallelogram. Were there some other things that also happens when you have a parallelogram? Nick? Opposite sides are congruent. Good. What else? Ben? Opposite angles are congruent. Good. There's one more thing. Nick? Not the diagonals are congruent. The diagonals do what? Starts with a B? Bisect. The diagonals bisect each other, which makes a midpoint, which makes congruent parts, right? So those are your main things to remember. Now, there's a few ways to, combine certain of those properties, and they become other theorems that we talk about. So our first theorem, and these don't have names, they're more just descriptions. So if you use them in a proof, you can kind of just shorthand them, right? Write like a brief summary. I don't expect you to write out the full statement all the time. But our first theorem is if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if both pairs of opposite sides are congruent, that means we have a four-sided shape. All right, you have a four-sided shape if both sets are congruent at the same time, then you know it is a parallelogram, right? So top and bottom, left and right. If you can show that both sets are congruent, then automatically it is a parallelogram. If one pair of opposite sides of a quadrilateral are both congruent and parallel, then it is a parallelogram. So in this situation, if you can show me that just one is both parallel, sorry, that's supposed to be a little arrow. If you can show me that just one set is both parallel and congruent at the same time, then that also works. If both pairs of opposite angles of a quadrilateral are congruent, then it's a parallelogram. So again, that goes with your opposite angles property, right? If you can show me both sets are congruent, then that works. And then last way is if the diagonals bisect each other, then it's a parallelogram. So it's just taking those almost like, they're very similar to the theorems we talked about in 5.1, just kind of worded slightly differently. Those ones were almost like if something's a parallelogram, then this is what you know about it. This is you have some random quadrilateral. How are you going to show it's a parallelogram? So then this last one is that the diagonals, if you have that they bisect each other, if you can show that that point in the middle is a midpoint, then that will work as well. Okay. So again, they're just phrased slightly differently. If something's a parallelogram, then you know opposite angles are congruent, opposite sides are congruent, opposite sides are parallel, diagonals bisect each other. If you have a quadrilateral, then to prove that it's a parallelogram, both sets of opposite sides congruent, both sets of opposite angles congruent, diagonals bisect each other, or one set is both parallel and congruent at the same time. Or you could show that both sets of sides are parallel, because that's literally the definition of a parallelogram. Okay, so then what I have here, just rephrasing that for you, those are the 5 different ways to prove a quadrilateral is a parallelogram. Is just proving that one set of sides is parallel ever going to be enough? No. Does someone know another kind of shape that has one set of parallel sides? Julia? A trapezoid, right? What would you have to distinguish that, right? You need more things in addition to that. Is it enough to just say that one set of opposite sides is congruent? No, that could be anything, right? Triangles can have two congruent sides, right? Anything can do that. You have to show that both sets of opposite ones. So things like that, this is very useful to have if you're doing those proofs. So we are going to practice this by writing a little paragraph proof here. Okay. We are given a parallelogram ABCD. So that is saying that ABCD, that is this outside shape, that it is a parallelogram. That means all those properties apply. We have that M and N, so M and N are midpoints. We want to prove that AMC is a parallelogram. That's that inward, that inside parallelogram. So in order to prove that that inside shape, AMCN, is a parallelogram, you're going to have to pick one of these things and show how it could happen. Okay? So thinking about what we're told in our given, what are some things we could say? Let's start to kind of plan it out. What are some things we can say if we know that ABCD is a parallelogram and M and N are midpoints? Matt. AM is congruent to CN. How are we going to be able to say that? Mm-hmm.
Where AM is half of AB, CN is half of CD, and you.
Very good. Yes. So what we're going to be able to say here is DC is congruent to AB, right? We know that because it's a parallelogram. And then N and M are midpoints, so DN is going to be congruent to CN, and AM is going to be congruent to MB. Now, what Matt just said is that NC is half, right? And AM is half. And if they're both half of equivalent things, won't they have to be equal to each other? Okay, good. So that's something we'll need to say. And also, too, something to keep in mind, guys, this is a paragraph proof. So those tend to focus on key steps. I'm never going to mark you off for including more detail, okay? But keep in mind a paragraph proof is more like key steps. So you won't have to show that DC is congruent to AB. We can imply that because we already know it's a parallel. Okay, so let's start with that and let's see where we can get from there. So let's start by saying that NC, we're going to say that NC, you said that NC equaled, you said, like you phrased it with half, right, Matt? We're going to do that same thing. Okay. Actually, we do need to say that those top and bottoms are congruent or equivalent. That way we can use our transitive property. Now, the one thing that's also nice about paragraph proofs, normally if we're doing our 2-column, we have to do that whole progression of they're congruent, right? Then if they're congruent, they're equal and all that, you can kind of skip that in your paragraph proofs. We can go right to saying, since you have parallelogram ABCD, then I'm going to say that DC, the measure of DC is equal to the measure of BA. I don't have to say they're congruent. I can go right to measure since we're doing key steps. Okay, so I know that. And then we know that because M and N are midpoints, NC is going to equal half of DC, and AM is going to equal half of AB. And obviously, if you're writing this on your own, there's a lot of different ways to phrase this. Okay. Now, if DC was equivalent to BA, can we then now assume that NC equals AM? Yeah, does the half really change anything? No, because there's a half on both of them, right? That'll stay equivalent. So because M and N are midpoints, NC, the measure of NC equals 1/2 the measure of DC, and the measure of AM equals 1/2 the measure of BA. So the measure of NC equals the measure of AM. All right, so that's good. We now have that these two sides here are congruent, or that their measures are equivalent, either way. Good. That's one thing. We now have one set of congruent sides. What else could we maybe do? Julia? Good. How are we going to show that they're parallel? Yeah, very good. Yeah, isn't NC just part of our full line here, right? So if CD is parallel to BA, can we then imply that NC will be parallel to AM? Yeah. You could talk about how N is like collinear to D, N, and C. That something like that could be a good idea, especially if it was a 2-column proof. You could say that D, N, and C are collinear, right? That would just be the definition of collinear. Therefore, N would have to lay on the same line. I'm going to go ahead and say that since it's a paragraph proof, we can kind of skip that and say that since segment DC is parallel to segment BA, and N, well, we can skip that part. I was going to say and N lies on segment DC and M lies on segment AB. You could do that if you wanted to, but I'm just going to say that since those two are parallel, then we can go ahead and imply. So then NC is going to be parallel to MA. Good. Now we have that they're parallel and congruent. So is that enough to say that they're a parallelogram? Yeah. So we just now need to do our proof. So I'm going to say therefore AMCN is a parallelogram because, and then we would use our second theorem up here, one pair of opposite sides is congruent and parallel. You don't have to write out the full statement. I would probably find a way that you like to abbreviate that. I'm going to say because, and I'm just, oh, sorry. I keep hitting my keyboard today. So because one set of sides is both congruent and parallel. Good. And there's definitely more than one way to do that. If you didn't think about the 1/2 thing, could you have maybe done some segment addition, right, with DN and NC? That would also work. You could also do it by saying DC, the measure of DC equals DN plus NC. and the measure of AB equals the measure of AM plus MB, and then subtract out any equivalent parts that you would have, right? Set those equals, subtract it out. So that's another way you could do that, but this is just one example. Okay, so you use it in a very similar way that we did with the triangles. In 5.3, we have a few different theorems here. So we have, these theorems all have to do with parallel lines. So the first one is the equidistant parallel lines theorem. It says if two lines are parallel, so in our diagram here we have line L parallel to line M, then all points on one line are equidistant from the other line. Now think about it logically. If two lines are parallel, right, they're always the same distance apart. So what this is saying is if you pick 2 points kind of in corresponding places along your lines, they're going to always have to be the same measurement. So this is implying that if line L is parallel to line M, so we're going to say, and we're just going to kind of write out a little explanation for it. So if line O is parallel to M, then you're going to know that the measure of AC equals the measure of BD. That's what this is saying. And it says equidistant, so you can use their measures. So the measure of AC equals the measure of BD, which should hopefully be reasonably logical, because if they're parallel, right, that measurement between them is always going to stay consistent. You'll also notice the right angle symbols here. Anyone know why those are there? Sebastian? Yeah, well, and yeah, exactly. Because if one's at a different angle than the other, right, those aren't going to be, that's not the shortest distance. The shortest distance between a point and a line is always that parallel segment. So that's to show you that they are parallel. Good. All right, good. 3 parallel lines theorem. 3 parallel lines theorem says, if 3 parallel lines cut off segments on one transversal, so here are your 3 parallel lines, it's saying that they cut through one transversal, like AC, and see how they're cutting it into little smaller parts? Then what happens is they cut off congruent segments on every transversal. So if these 3 lines are parallel, then we can imply that congruent parts are cut off on either side, basically. So, for example, if we know that segment AB is congruent to segment BC, then what do you think we can imply on the other side? Logan? Exactly. Segment DE is congruent to segment EF. Yeah. And not necessarily that the opposite sides are congruent, right? It's not necessarily going to be the case that AB is congruent to DE, but if basically this is saying if they're congruent along the one side, they will have to be congruent along the other side. Okay. Any questions about either of those? And if you guys want, if it's going to help you later, we can write a little statement here. So here we would say if segment, or if line AD so if line AD is parallel to BE, is parallel to CF, and segment AB is congruent to segment CB, then segment DE is congruent to segment FE. That's what that's saying. If they're parallel and they cut off congruent parts on one side, they cut off congruent parts on the other side. And that's an E. I know that that's a very sloppy E. There. Good. Why do you just keep coming and going from the meeting? Okay. We good with that? Can I move to the next page? Okay. No? Oh, no, you're fine. You can keep copying it if you're not done. Okay. All right. Parallel mid-segment theorem. Mid-segment. I like that vocab word because it sounds like exactly what it is. Mid-segment, it's the segment in the middle, basically, the midpoint, right? I'm just going with what it sounds like. But that one should be kind of easy to remember. So we have two theorems that deal with mid-segments. One has to do with parts being parallel, and one has to more deal with congruency. So the parallel mid-segment theorem says a line that contains the midpoint of one side of a triangle is parallel to another, and is parallel to another side, passes through the midpoint of the third side. So the phrasing on that's a little goofy, but what this basically means is if you have a segment, like for example, DE, if that contains the midpoint of one side, so for example, if we know D is the midpoint of side AB, and how would I know it's the midpoint? What would I see if D is the midpoint? What will I know? Nick? Exactly. BD would be congruent to DA. Okay. So if I know that that one part, that D is a midpoint, and D lies on segment DE, and if I know that DE is parallel to AC, then I'll be able to know on the other side, BE is congruent to segment CE. Very similar to the last theorem we just talked about, just a slightly different diagram associated with it. So if D, I'm going to say if D is the midpoint of segment BA and segment DE is parallel to segment AC, then we know that segment BE is congruent to segment CE. Okay. So that's what that theorem basically tells you. If D is the midpoint and those two lines are parallel, then the other side is also congruent. Again, very similar to the last one that we did, it's just not dealing with three separate lines. Questions yet? I feel like these are ones that the theorems themselves are worded a little tricky, but then hopefully once you apply it to a picture, it makes a little bit more sense. Okay. And then the next one is just the basic triangle mid-segment theorem. It says that the segment that joins the midpoints of two sides of a triangle is parallel to the third side and is half as long as the third side. So this is saying you have this segment here, DE. Basically, if this is your mid-segment, and if it's your mid-segment, you'll know that D and E are both midpoints. So you'd have congruent measurements here and here. So if you know that, if DE is the mid-segment, then first of all, you're going to know it's parallel to the other side. You will know that DE is parallel to AC. So you will know that DE is parallel to AC. Okay. And its measurement will also be half as long as the third side. So the measure of DE will equal 1/2 the measure of AC. Again, think mid-segment, middle, half, right? It all kind of goes together, hopefully. Questions on any of those theorems? Make reasonable sense so far? Yes, Ben. So it's half of AC. You have to think of it like, again, like everything's a mid-segment, right? So it's the middle measurement. As far as why it is, well, if it cuts both of the opposite sides in half, it's a trig property about like how all the sides of a triangle are related to each other. I can look up exactly like how it works and explain it to you. Off the top of my head, I don't know that trig rule. But in my opinion, the best way to kind of remember it, right, is if it cuts either side in half, this third side AC isn't getting cut in half. So you can just think of it, it's half of that. Okay, but I can always look up that rule. I just don't know what it is off the top of my head. Yeah. All right, let's look at a quick example. And then you guys are going to have a lot of time to do your homework, which is nice. So, do you have a question, Luke? You sure? You sent me a question mark. Yeah. Interesting. Just realized I didn't turn my camera off. That's okay. Okay, so points X, Y, and Z are midpoints of segment B, are AB, BC, and AC. So we know we have some midpoints here. So the first thing I would do is probably go through, do some labeling. If X is a midpoint, you'll know these are congruent. If Z is a midpoint, the measure of your measures here are congruent. And then if Y is a midpoint, your measures there are congruent. If the measure of AC equals 24, it wants you to find the measure of XY. We just saw a theorem about that. Any ideas? Julia? How's it 12? Exactly, yeah. The measure of XY is just equal to half the measure of AC. So that is going to have to be 12. Good. So if the measure of AB is K, if the measure of AB is K, what would YZ have to be, Sebastian? It is, yes. You could say 1/2 K, you could say K over 2, whatever you prefer. Good. If the measure of XZ, so XZ is this segment here, if that is 2K plus 3, what will BC have to be? Matt Sandrick. How'd you get it? Yeah, just double it, exactly. When I was walking around, I saw a few people had it like this, right? Like distribution. That's good. Just make sure you like actually go through and simplify. Luke? Oh, okay, sure. 1 second. So this would be 4K plus 6. And then last one, part D, says if the perimeter of triangle XYZ is 24, so XYZ, that's this small one in here, then what is the perimeter of triangle ABC? What'd you think? How'd you get that? Multiplied it by 2, okay. I see where your strategy came from. Oh, well, I saw some different numbers when I was walking around. So, okay, so some people went ahead and multiplied it by 2. Did anyone do it differently? Did everyone get 48? I didn't think so. When I was walking around, I saw some different numbers. So I'm curious because I think you guys got 96, right? I think that's what I saw when I was walking around. Well, let's see what makes, well, let's talk about it. I don't know. How did you guys get 96? Matt? Why would the area be 96? Right. This is true. So how did you guys get 96? I'm just trying to figure out how we all got our numbers. I'm not telling you which one's right or wrong yet. Well, no, what did you do to get 96? Lucas, what did you do to get 96? Oh, okay, I see. Yeah, Sebastian. Why? So, okay, so no. So I see where you're getting confused. Maybe. It doesn't necessarily say that it's an equilateral triangle. So you can't assume that. But, however, Matt is right when we say that that each side, right? Isn't it just it's double the mid segment part? So yeah, Luke was right. It is 48. Does that make sense though, guys? Because isn't each side double its mid segment, right? So yes, you would just double its measurement. So it would be 24. Do we see how we got that? Luke, why are you joining 1,000 times? You're driving me bananas. No. Remove from meeting. Remove. I mean, the Google Meet's over. So, like, why? Almost. Yes, I see your hand up, Logan. Sorry, I'm trying to kick Luke out of this meeting. What's up? Yeah, I did mean to write 48. Sorry, I'm a little distracted by someone who sits in the front row. I wonder. Let's see. Settings. Host controls. It doesn't matter. We're already done. So I'll figure out how to lock Luke out of the meeting later. All right, so this should be 48. Thank you, Logan. Okay. People at home, any questions? Yes, I see that, David. There are 4 Lukes. There's only one, but he counts like 4 people. All right. How are we feeling about it? Okay? Okay. So your homework for tonight on the 5-2 part, there are a few proofs. On the 5-3 part, I didn't give you any proofs with these. It's just trying out the properties and applying them. Okay?